So, well, basically, it's a work that we've been doing with like Yannick, Matthieu, and Nicolas to finally have good eliminators for nested inductive types, because so far in Rocq, they were basically more or less pointless. So, quick recall about inductive types. You define your inductive types in Rocq or lean, like list. All is reasonable. To be accepted, it needs to satisfy a positivity criterion so that the logical consistency of the system is preserved. And then basically for every inductive type that is positive and is accepted, automatically an eliminator is going to be generated. So for the list, you just get the usual one saying if the predicate is true for the empty list and for every element, every smaller list is true, then it's true for P of A.L. You actually get one eliminator per sort. So here we have the one for prop, we can get the one for S prop, and so on. And so in Rocq, these elimination principles are generated automatically as combination of fix and match, because those are the primitive constructors in Rocq, and in lean it's the eliminators that are primitive. And so it's the opposite. It's a function in fix and match that are going to be elaborated to eliminators. So what are nested inductive types? You may very well have seen the most common example of n-ary branching trees, also known as RoseTree. It's just basically saying a tree is made of a list of subtrees and so on. So it's n-ary. And it's so-called nested because basically RoseTree that you're defining appear nested inside another inductive type, which is list. And so these kind of inductive types are very useful because basically they enable users to have a more sophisticated form of recursion. You have lists, so you can have n-ary operators like match or switches. You can nest with option to be able to have an optional recursive argument and so on. And for these reasons, it's used in all the major computer science projects like MetaRocq, VST, Iris, and so on. It's mentioned in the stuff that Lean needs to fix to finally be a good setup for computer scientists. Because the reason is that it enables to reuse libraries. For instance, if you have a basic function map on list and you want to define a function on RoseTree, you're just going to say, okay, I have a list of RoseTree. I apply my RoseTree map function recursively with the function map for list. And this way you define one library for list, for the containers you're nesting with, and you can just reuse them. So RoseTree is very simple, but you can actually really quickly get into very complicated nesting. For instance, if you just define like a notion of term, like some syntax, with an n-ary operator, like a switch, like a generalized if. Then if you want to define what's a typing derivation, you're gonna want to say, oh, all the branches of my switch have the same type. How do you actually do that if term is already nested? Well, you're gonna define an inductive predicate, all, which is basically the empty list satisfy the predicate, and if all my element pointwise recursively satisfy the predicate, then my list satisfies it. And then if you start defining typing derivation, you're gonna say, oh, all my branches have the same type, which is return type. And so here typing is actually getting nested with the all predicate, which is a predicate on list. And so the lesson is basically that if your object you're manipulating is nested, so is going to be your specification. And this quickly gets very complicated in real-life examples. For instance, in MetaRocq, the definition of typing is about 100 lines. It's nested 15 times in 15 different ways, with sometimes several depths of nesting and several nested inductive type nested. It's kind of a mess. And you just need good support for that if you want to do this kind of stuff. So they're really useful, and yet justification for it is very folklorish. For positivity, it's just say, oh, they are mutual inductive types. And that's the folklore. For eliminators, they say, oh, it's some form of parametricity. I'm sure Wojtek can tell you about it. And so scaling that to dependent types is actually a real issue. So I don't have too much time to review that, but neither support for Rocq or Lean is actually very good. What they do in both cases, they say, oh, nested inductive types are mutual inductive types. So we're just gonna, to see if we accept nested inductive types, we compute the mutual encoding, and we see if it's positive or not. Turns out neither Rocq nor Lean actually accept the same stuff. Lean is too restrictive and reject the typing example I've just shown, even though it's very basic. And Rocq is quite amazing because it manages to be both times too restrictive and too lax. So it's too restrictive. For some reason, you can only nest with non-mutual inductive type. Why? We don't know. And it's too lax because there's a bug, and you can somehow make some very particular inductive types accepted. Because basically they forgot to check, and that happens. They wanted to be smart and they got dumb. And so in each case, you still have this weird dynamic check, and it does weird stuff because it's dynamic. And so what happens is that if you define this type depends on B, just takes a Boolean and a type A. And you're like, wow, I would like to nest on A. But basically you say if B, then A, else A to bool. And so basically if A is going to be true, this reduces to A, and A is positive. But if B is false, then it reduces to A to bool, and then A appears on the left of an arrow, so it's not positive and you can't nest on it. And so basically, this type is going to be rejected, but this type is going to be accepted. Because it's going to compute a mutual encoding, start doing reduction, see that, oh, you have if true, so it actually reduces to A, and that is accepted. That is not really modular. That is really not great. If you had some crazy positivity annotation, maybe you could say, oh, it is positive only if B is true or something. But in real life, it's really complicated, and we don't know to do that nicely. And then for eliminators, it's a mess. Lean basically just gives you the eliminator of the mutual encoding and beautifies it. There's no reason for it. It just beautifies stuff on the fly with no justification. It does not compute as you would want, so they just add reduction rules. And why they do that? They do that because eliminators are primitive in their system. So they just can't afford to give you an eliminator that is trivial. Unfortunately, it does not work really well because the encoding clearly leaks. It blows up in size, despite the restriction that prevents typing from being accepted. And the R part, which is actually instantiating this eliminator, you still have to do it. And Rocq, well, they just decided that if we don't know what to do, we do nothing. So if you look at the eliminator for RoseTree, it's just going to say, oh, I have a list of RoseTree. I don't know what the induction hypothesis is supposed to be, so I'm just going to do nothing. So it's not so bad because you can always write it yourself with fix and match because there's some support in the GARP for it. Don't ask me how, I don't know. But basically, you're just going to say, oh, if I have a predicate which is always true, then the parametricity is true. The whole predicate is true. Makes sense. If the predicate is always true, it's true pointwise, so it's true. And then you just define your induction principle by saying, oh, if I have a list and my predicate I'm trying to prove is true for all the elements of my list, then I can prove P of node. And then you just prove it by fixed point. Let's just say it's very, very tedious. So for typing of MetaRocq, that's 100 lines of code, and the proof is 350 lines of code. So basically, you have to write 400 lines of boilerplate, 500 lines of boilerplate for a 100-line definition. That is awful, and I think we could remove several 1,000 lines in MetaRocq if we could get rid of that and generate them automatically. There have been some work by Enrico Tassi using parametricity, as the folklore says, but sadly it does not work really well with type dependencies. So now let's get to our work. So basically what we did is that we've identified a subset of well-behaved nested types that can be determined syntactically to be positive. You don't need to compute the encoding. And syntactically, you can ensure that there is an encoding. And this subset basically covers all the basic examples like RoseTree, like typing. It's modular, and it has the very nice thing to rule out these ill-behaved types that really rely on the dynamic behavior. And once you've done that, basically you end up with a class of inductive that you can always generate a whole predicate for, and that you can always generate an eliminator for. And so we've implemented this in Rocq. It's been merged last night, so it will be part of Rocq 9.2. So if you look at the list, Now there's a common scheme all that is going to generate this list all predicate we've seen. So it's a bit messy, it's sort polymorphic and so on, because we have different sorts in Rocq. So we need to be able to instantiate it with prop, with type, and so on. But it's just the usual thing that we've seen before. I have a predicate P of A, and I say, oh, for every element of type A, I have a proof of it. I'm just enforcing point-wise that my predicate holds. Then you have the theorem we've seen before that just says, oh, if the predicate always holds, then this always holds. And then if you define RoseTree, you're now going to be able to get the good eliminator. You're going to say for all lists, such that P is true for every element of the list. Then I can conclude that my property hold on the node. Then I can conclude that it's always true for all the RoseTree. And this list all for all is just going to be here to inhabit the fixed point. And it's really modular. If you start doing weird nesting like this, like here you nest with list, but functions of Boolean into list, so you have double nesting plus function, you're just going to get the good eliminator again. Well, it's a bit ugly, but when you do working with MetaRocq, it gets ugly, you know. And so basically, the key thing is like this new positivity condition enables you to tell what is important, what is recursive or not. So for vectors, for instance, scheme all is just going to be doing stuff for the type A. It's not going to do... I forgot a variable, no? Ah, no, right. I have to do a print. Yeah, so basically you're just going to say, oh, for all my element A, P of A must hold, but for my natural numbers n that do not participate to the specification and to the type you're nesting on, you do nothing. And that's the opposite of parametricity. And by being smart like that, you end up managing to get out of the type dependency hell. So then you can just have like a vectree, which is like every tree must have a fixed size. You can also nest with prod. Something nice is that now there's a new setting to make the generation automatic. So if you just write set def scheme all, it's going to generate this all predicate twice. It's going to generate prod all, and it's also going to generate prod all, which is the prod all predicate for prod all, which can be useful when you start having a bunch of layers of nesting. This is going to work great. And finally, something that happens very often is that you nest only on one of the parameters. Here for product, you nest on A, but not on B. What happens is that it's just going to inline a predicate fun true for the predicate that you need to give, but that you have not nested on. But there is also a scheme command to generate all predicate only for some parameters. So here, for instance, we can say, oh, I want an all predicate, but only for the parameter A. And in this case, you're just going to end up having like, oh, I have my type A, a predicate on it. I have my type B. I don't want to nest on it, so I'm not generating a predicate for it. And I just get the prod all without the predicate on B. And so once it's registered, if we look at the induction principle, if we regenerate it, we are now going to have prod all 10 of left tree. 10 is for 1, 0. It's like A but not B. And you won't get this fun true that is was basically around before. And so it's quite nice for a few inductive types that you only nest on some parameters, even though a bunch of them could be nested.
So how do you tell that you want to use this new asymmetric prod all version?
Well, for instance, in MetaRocq, they have a... Oh, it's quite simple. It looks at all the arguments. Yeah, it looks at all the arguments, check which one are nested, look if the specific one has been registered, and if not, it just falls back on the general one. And if it's not found, it just creates a warning saying your eliminator is pointless. Voila, and then it works on typing. You're just gonna generate the all scheme for list all, and then you get at the twice level because you have your typing derivation which is nested with something that is nested. And then if you generate the inductive predicate, you're then gonna end up having list all of all that appears. And it scales really well, so we're quite happy. For the moment, this default is set to 0 for two reasons. First, there's a few repository in the CI that needs to be fixed. For instance, some MetaRock has a problem with sort polymorphic definitions. And hopefully in Rocq 10 or 9.3, this will be set to 1, and then we're going to get nice eliminators by default. Voilà.
I'm not convinced.
I'm not surprised.
You choose the all approach, but why would the all approach be the one that your user wants to have?
Well, basically, we've still shown in the paper that like this eliminator can prove the eliminator of the mutual encoding and the opposite. So basically, we know that this eliminator is a valid one. There might be different formulation of it. You may want to define this list all as a fixed point, but basically it's a register scheme comment, so you can always choose not to register it, not to generate it, and register a custom one. It just needs to have the expected type.
But I had the impression that you might want that when processing the list, you might want to inherit something from the first elements in the processing of the flowing ones, like in fold or something like that. So in that case, it looks like your all approach is going to miss some computation power.
So what you say is true, is that there's always a more specific inductive principle that we can have, but the same way as the inductive principle with list is supposed to be universal and enable you to prove everything, including the more specific one that you would want for your problem, this one should be able to do that. Sorry?
For all n list of n and p of list of nth list of n. Sorry, you have the all expressed within an indexing with a for all n p holds that for the nth element of the list.
Actually, it's much more complicated.
Oh no, it's for many applications this is what you want.
Yeah, maybe.
Because you're indexing, you're thinking of that list of thing being a vector, and you want to index with it. So whenever I have to define these predicates, this is usually the form I use.
Yeah, but basically what you would have to do that is to like specify, if I understand correctly, you would have to define what it means to be in a list or stuff like that. No? You say for all element in the list with an in predicate?
Oh, for all index n, the nth p holds for the nth element of the list.
Yeah, but then you have to define nth and so on. It's not so easy to define.
But you have nth.
Yeah, you have nth, but like how do you define nth for typing? It's just that like list is so specific, there's a bunch of ways to reason about it, but if you really want to be systematic, I don't see any other way, and we've proven that it works. So it's systematic, not necessarily the best option for what you want to do.
Last one.
Is the list...
Can you debate one?
Okay. The list all, I didn't quite understand why you needed double. Why can't you use list all of list all?
List all of list all?
Yeah, like nesting, because list all takes a thing on like data prop and then produces a list data prop.
Maybe you want me to show you what
list all of the thing, wouldn't that give you what list all does?
List all, so list all, it's the all predicate for the inductive type list all. And basically it's saying, oh, if I have A and a predicate, which is going to be typing, and a predicate on typing, then I can prove that my list all is holding. And the thing is that when you're working with MetaRock, in most cases, you're actually going to be non-dependent for your specification. In this case, this list all can basically be brought down to list all up to one issue, which is basically that like the common definition of list is not sort polymorphic. So if I'm non-dependent, I still can end up in prop or S-prop or something. So I can't just instantiate list with S-prop since it's going to type. And so this issue is basically why we have to generate it automatically. But there really are better instantiation depending on what you're doing.
usability question. So assume in my library I already have a definition of list all that I handwrote in prop, but I don't have one in type. Is it possible to your setup to register my custom definition for prop while still using your auto-generated definition for type?
No, it's not supported.
Okay.
It actually didn't really arise because... No, it didn't actually arise because... Yeah, I guess we could do that.
Okay, I think we need to stop now, but
Yeah.
thanks again.